This is the third part of chapter 13, the last section, and we are going to talk about allylic halogenation and then addition to alkenes, polymer formation, and oxidative damage by radicals. So that sounds like a lot, but allylic halogenation is really just a variation of the reaction you just learned, halogenation of alkanes. So the reagents are specifically NBS and bromosuccinimide with light or peroxides. And chlorosuccinimide doesn't work so well. So generally we talk about allylic bromination. What NBS does is to produce a bromine radical. It also reacts with HBr formed in the reaction to generate Br2. So this is a source of a low concentration of Br2. The allylic radical is more stable than a tertiary radical, and that is because of resonance stabilization. And you have to be able to draw the resonance forms because each form can lead to a different product. So the mechanism, again, really the same as the mechanism we've already gone over, except your initiation step is cleavage of the nitrogen-bromine bond to make a bromine radical. Okay, there's another reaction where NBS can react with HBr once you have a little HBr present, and that's going to generate Br2 plus succinimide. So that's where your source of Br2 comes in. Once you've got the bromine radical, then this abstracts a hydrogen and you generate a radical. So in this case, I've written in two of the hydrogens. So this is 1,2-dimethylcyclohexene, and I could make a radical up here on this methyl, or I could make a radical at the allylic position. There's two other secondary places where I could make a radical. And all you're going to do is generate allylic radicals. So allylic, going back to chapter 10, remember, is the position next to an alkene. Okay, so what I've drawn out here is formation of the secondary radical. Once I generate the secondary allylic radical, the other secondary radicals just aren't even going to form, okay, because they are not nearly as stable as the allylic. So this has a resonance form. Once I have this radical, it's next to a pi bond, so that gives the resonance form on the right. So those are the two resonance forms for the allo radical. Either one of those can go on in the next step to add to Br2 to generate the product. So the bromine is always going to end up where the radical was. So this is one product. And then the other resonance form gives a different product. So you could also write this out for formation of the allylic radical on the methyl, and I would recommend that as a practice problem. I look at a couple of examples. I have 1-butene, and with NBS and light, I'm going to generate the allylic radical, and the resonance form is going to look like this, where the double bond is in the center and the radical is at the end. Each one of those is going to go on to give a different product. So you would get two constitutional isomers as products based on the two resonance forms. With this next example, again, I'm going to generate a allylic radical that has a resonance form now I've got the double bond in the ring and a radical on the methyl. Each one of those can give a different bromination product. So if you have forgotten resonance forms, you want to go back and practice that. From here on out in 3020, you're going to see lots of problems that involve resonance forms. Another reaction that can happen is addition to alkenes. So if I have one butene and I react this with HBr and peroxide with light or heat, you get anti-Markovnikov addition of HBr. So I end up with the bromine on the less substituted end, hydrogen on the more substituted end. Going back to chapter 10, if I had one butene and react with HBr, no peroxides, then you get Markovnikov addition, and the bromine ends up on the more substituted end. So you get a different product because it's a different mechanism. HBr addition without peroxides goes through the more stable secondary cation. So you add the hydrogen first, and then the bromine adds. In this case, you're going to add the bromine first to give the more stable radical. Initiation step is cleavage of peroxide, which can react with the HBr to give a bromine radical. Once I get that radical, it can add to the alkene to generate the secondary radical. You're not going to get the primary radical. And then that pulls a hydrogen off of HBr, so the hydrogen comes from HBr to give the anti-Markovnikov addition. This type of addition is also seen in some types of polymerization. So I'm not going to talk a lot about polymerization. Typically, polymers are formed either by a cation polymerization or more often by radical polymerization. These are initiated with peroxides, and you generate a radical from initial addition to the alkene, and then that just keeps adding to your supply of alkene. So polymers is a whole separate area of study in organic chemistry, and the type of product you get depends on the temperature, reaction time, physical conditions. So there are different types of polyvinyl chloride, polyethylene, polystyrene. These are all polymers of alkenes. So this is just showing an example with styrene, which has an arabenzene ring attached to an alkene. So if you add a peroxy radical, that's your initiation step. You generate a carbon radical. And as long as you've got a supply of styrene, and the pH here stands for phenyl, which is the benzene ring. Okay, so I've abbreviated in the rest of the structures. That radical adds to the next molecule of styrene. So I have my sort of initial piece here. Now I've added another piece. This radical is going to add again. So now I've got my initial piece and then my second piece. And again, this can keep adding, and you can sort of pick out the different pieces here where you've got a phenyl and two carbons, and this will just continue on and on and on to give polystyrene. So the last topic is antioxidants and oxidative damage. So your book has bigger pictures of lipids, but lipids are alkenes, so they're fatty acid esters, and you know that if you, for instance, leave butter out, it is going to get stinky, and any type of food with fats in it is going to degrade, get oxidized, and this is coming from reaction of allylic radicals with oxygen. So some food preservatives are antioxidants. These are usually phenols, and what they do is scavenge radicals and prevent this oxidation. So this is just a general reaction. If I've got a lipid, it'll react with oxygen to give a radical that adds to another molecule of oxygen, and now you've got a peroxy radical that can go on and prevent further or cause further damage, and this is how fats degrade. So vitamin E is a naturally occurring phenol. This compound at the bottom is just phenol itself. BHT is an alkylated phenol that's used as a food preservative. And what these are is radical sinks. So these phenols will react with a radical that's been generated to give a phenoxy radical. This has multiple resonance forms. So I can push this electron in toward the aromatic ring. That gives me my next resonance form. This has another resonance form. And so on, and you might want to practice drawing the next one. So because there are so many resonance forms, this is very stable, and phenol, like I said, is a radical scavenger. Another type of naturally occurring degradation by radicals is oxidative DNA damage. So reactive oxygen species in your body are produced by respiration. So those would be peroxy radical, peroxide oxygen radical. So ROS just means reactive oxygen species. And these can react with DNA bases and leads to oxidation. The most common one is called 8-oxo-G. So this is 8-oxoguanosine, and as you age, more and more of this builds up. And what is the problem is that 8-oxo-G forms the wrong base pairs. Usually what you have is what I've got drawn here on the top. This is just a picture of DNA showing the different bases. So you've got adenosine, thymidine, guanine, cytidine, and you've got the DNA backbone with the different bases that are circled here. So in your DNA, these hydrogen bond to each other, the bases, and that's what holds your DNA together. So thymine pairs with adenine, guanine pairs with cytosine. So this is just showing the normal base pairing. Guanine can get oxidized to 8-oxoguanine, so it has a ketone in the 5-membered ring. That leads to mispairing. So 8-oxo-G, instead of pairing with cytosine, will pair with adenine. And that leads to misreading of DNA. It leads to mutations. It can lead to cancer. So this is a problem. So again, this is one of the reasons why antioxidants are good for you, because they help scavenge these reactive oxygen species. So that's where we're going to end for radical